Welcome back to the Ergo blockchain crash course video series. In this video, we're going to cover the anatomy of the Ergo blockchain. So the outline for this video consists of the anatomy of a box, a transaction, an address, a token, a block, and finally a wallet. So for the first part, the anatomy of a box, we'll consider the registers. Each box consists of 10 registers. The first 4 are predefined, so the first R0 being the value, R1 being the script, R2 being tokens, so any additional assets in the box, and then R3 being the creation info, so information about how the box was created, so the transaction block height, the transaction ID, and the output index, so the position in the outputs of the transactions that created it. And then R4 to R9, the final 6 registers can be arbitrary data that you want, as long as it's a valid Ergo script data type. So even though you can have arbitrary data in a box, you are limited by a maximum size. So, and this size is 4 kilobytes. So all of the data in the sum of all of the registers, if you sum up that number, it must be less than 4 kilobytes. So all erg in a box is represented in nanoerg, so a billionth of an erg, and you need a billion nanoerg to have 1 erg. So, and all unspent boxes must have a minimum amount of erg in order to exist. So you can't just create a box with 0 erg in it. It must have some minimum amount, and that number is a million nanoerg. And finally, once a box is spent, it can no longer be used as an input into a transaction. So when you're designing a transaction, there's a few different box types to consider. The first being data inputs. So these are boxes that are not spent. So they get used in order to read some data information stored in them, and since they're not spent, they can be referenced by multiple transactions in the same block, which is kind of cool. And then the other important one are inputs, and these are the actual boxes that will get spent, so they can't be used again in another transaction. And finally, we have the outputs, which are the new boxes created, and these ones can be spent in other transactions or just left on the blockchain and not get used up at all. And then they'll be subject to storage rent. So that's it for the box. We're going to now cover the anatomy of a transaction. So I'm showing here in the diagram the different boxes that are part of an actual transaction. So you might have data inputs if that's what you needed. You'll for sure have input boxes that need to get spent. And aside from the register data that's in them and any variables stored in the contract itself, additional data that you can provide to the box are context extension variables. And these variables get attached to the box right before it gets executed. So unlike register data, which is inserted into the box when it's created as an output of a transaction, and then that box can no longer be modified, and it can only be spent or unspent. But if it is to be spent in another transaction, you can attach extra data to it, and that's what a context extension variable is. And so if you were to sum up all of the erg in all of the boxes, the input boxes that are going to get spent, and then that amount must be equal to the erg in the output boxes. And then the new output box is the miner fee box. So this is used in order to pay the miner who submits the block with your transaction in it. And usually the minimum miner fee is 10 million nanoerg. And since there's a parameter that can be voted on, miners can vote to increase or decrease this number. So when you're talking about transaction cost, usually there are two types of transaction cost. The first and most common one people hear and talk about are the literal one, which is the miner fee. So that's the amount of Ergo you have to pay. And then there's also another one which is more of one that's used as a design limit, which is the computational cost limit of the transaction. So when you're like designing a contract or a transaction, that if your contracts are too complicated, or you have too much data you're dealing with, then it might exceed the computational cost, and you'll have to go back and redesign something in order to ensure that this type of transaction cost is not exceeded, so the transaction can be submitted to the blockchain. So in this sense, transactions on Ergo are deterministic. Everything about the transaction is calculated before it's ever submitted to the blockchain. You can calculate all of the miner fees the user will have to pay beforehand. The computational cost limit of the transaction, like I said, will prevent you from submitting your transaction to the blockchain. And as a designer, that's useful because then you know that something is wrong. And the transaction will only fail if it's not submitted into a block by a miner. So let's say you haven't exceeded the computational cost, everything is fine. You sign it, you submit it to the transaction, and then now you have to wait for a miner to include that transaction in a block and get it confirmed. So if that doesn't happen, then it will fail. But it's as though the transaction never occurred, because the notion of things occurring, so in some sense time, is defined by blocks being created properly. So if your transaction is not part of a block, it's as though it doesn't actually exist. Users' funds will not be spent, and you'll have to try submitting to the blockchain again. So in the sense, if transactions fails on the blockchain, it's actually it's not an unsafe situation for users, because nothing will happen. So we're going to cover the conservation of Ergo a little more in depth. So if you had watched the previous video on the UTXO model review, I mentioned that a good conceptual model to have is to think of a graph with nodes and vertices, and the nodes being the transactions, the edges being the UTXOs into a node and out of a node, so the inputs and outputs. And there's also something called the flow on the edges, which is just information flowing from one node to the other through edges. And in this sense, that information we can consider that to be the Ergo as well. And the Ergo into a transaction must be the same that is out of it. And this is one sort of mathematical definition of a flow, that usually the flow into a node must be equal to the flow out of it. And like I mentioned with storage rent, every 4 years, if the value in a UTXO is too low to pay the transaction fee, all the Ergo and tokens, as it's currently implemented, will then be recycled by the network, so sent to the miner of the block. And just as a quick aside, this is a fun physics analogies sort of slide. So in the same way that you have this concept in physics that energy can't be created or destroyed, similarly, Ergo cannot be created or destroyed. So what do we mean by destroyed? In Bitcoin, as we all know, if someone loses their keys, then that Bitcoin is effectively lost to the network, right? That's why people freak out when they lose their keys, because they can't recover their money, and nobody else in the network can as well. So it's as though, even though it's not literally burned, it's as though it's been burned. And Ergo, on the other hand, because of storage rent, if someone loses their keys and no longer has access to their UTXOs in their wallet, then after the 4-year period, some amount of the Ergo will get recycled to the network again and be able to be used by people. Now, it may take a long time for all of the Ergo and UTXO to be recycled, but recycled nonetheless. So Ergo is therefore a closed system, in the same way that a system in physics in which no energy escapes or enters, we call that a closed system. So what are the consequences of this? The blockchain doesn't need any sort of policy that would mint more coins into existence, because we fear that there might not be enough tokens to go around for everybody. And a million Erg is all there is, or ever was, or ever will be. So when the blockchain was created, there was only 1 million created. So the next topic we're going to go over is the mempool. So if you're a node running on a computer, then there will be some amount of memory in your computer that will be dedicated to putting the transactions in it before they get inserted into a miner's block for confirmation. So what is this useful for? So this is a sort of brief high-level recap of like what happens when you sign and send a transaction. So when you sign and send, it first goes into the mempool of a node that you're connected to, so that you're using to access the blockchain, and then this gets broadcasted to other peer nodes in the network. So everybody sort of gets a copy. Mining nodes, since they're also nodes connected to the network, will get access to these transactions in their own mempool on their computer, and they'll try to include these into a block, which they broadcast to get validated by other nodes. If the block is verified successfully, the transaction will be confirmed by mining and non-mining nodes and removed from the mempool. If the block is not verified successfully, the transaction will not be confirmed and fail. So it'll fail in the same way that I mentioned in the previous slide. It's as though the transaction never occurred, and so no funds are lost. Now we're going to cover the anatomy of an address. So on Ergo, there's different types of addresses. There's the network type. So depending on the network type, you'll have a different type of address. The mainnet address being where all of the real Ergos, and the testnet being where all the fake money is. So if you're a developer, you'll use testnet to try your protocols, your contracts out, see if they work or not, if there's any flaws. And in order to not worry about using real money, there will be fake Erg. And so in the same way that we can have different addresses based on network type, there's also different addresses based on the content or what the address represents. So the most common one is a pay-to-public key. So when you create your wallet, that address type is a pay-to-public key address. If you're a developer, you're writing your own Ergo script contracts, the address that gets created based on that contract is what's called the pay-to-script address. And we also have a pay-to-script hash, but this is less commonly used. So what is the actual structure of the address? So under the hood, it's actually just three values that get appended to each other. We have the prefix byte, which is the network address, plus the address type. So you could be mainnet or testnet, and then one of the three address types. And then the middle section is the content bytes. So this is where your contract, when it gets compiled, and then encoded into some bytes, that's what it is. That's the content. And then we have the checksum, which is the leftmost 4 bytes of the hash of the prefix byte appended to the content bytes. And then all of this is encoded in base 58. So now we're going to just cover what addresses and boxes and how they're related. So each box must have a script or contract associated with it, and thus an address. So each box will have its own address. The script contract is independent from the box. So thus multiple boxes can be created, each with the same address stored within it. in R1. So when you create a contract, all you get is this like string, and that's the address. But if you haven't actually created any box, or which you do by submitting transactions, then there's no actual box that exists with it, with that address. Even though you've created a contract and compiled it to produce an address, there's no box associated with it. So in order to for the box to exist and have something you could send money to or use in a transaction, you need to associate the box and the address together. So when you first create your wallet, for example, you'll get an address created for you, but there's no boxes or there's no Ergo in your wallet, and so that box with that address doesn't exist on the network yet. But if someone sends you money, then a box with your wallet address will be created and with some Ergo in it that they sent you, and now your box exists on the blockchain with your address in it. Now we're going to go over the anatomy of a token. So what is a token? In Ergo, a token in the most abstract sense is just a pair of two numbers, the token ID and the token amount. And then in Ergo script, the data type for this would be a tuple of the first element being a collection of bytes. So the token ID is just a byte array. And then the token amount is the long data type, so a signed long. So 2 to the 64. But then split in two, so you have the positive range. So then there's some rules you have to follow. So only one token can be minted per transaction. So, and by token, I don't mean the token amount being only one. I mean the pair itself. There can only be one created per transaction. And then the amount of a token out of a transaction can be less than or equal to the amount in. So it does not follow the same flow rules for the Erg, which must be equal in and out of a transaction. So in this sense, that's how you're able to burn tokens, but not Erg. So then the next two questions we want to answer are what is minting and what is an NFT. So what is minting? By definition of a token, we need to obtain the token ID. So how do we do that? So the minted token will inherit as its token ID the box ID of the first input box into the transaction. That's it. So in Ergo script, we can specify the token amount, and the output box will now have it in its token register a new pair, token ID, token amount, and that'll be the box ID of the first input box, and X will be whatever amount we assigned. And this costs nothing to do other than the miner fee, which I haven't included in this diagram, but is sort of implicit. And this cost is very low, so it's essentially nothing. And then finally, what is an NFT? So an NFT is simply the meaning we ascribe to the pair of the token ID, token amount. So, and specifically for NFTs, we set the token amount to 1. If the value was greater than 1, then we would just call that a fungible token. And so how do we ascribe the meaning? Well, this is why we create the EIPs. So EIP4 defines the S as standard EIP, which tells you how to mint tokens, what standard to follow in order to give them sort of attributes. What type of token is it? Is it an NFT for art, or is it some utility token, or is it meant to be used as a currency for a project? And then we have EIP24, which is the artwork standard, which is an extension of EIP4, and applies just specifically to NFTs that are to be used for art. And the purpose of the standard is to ascribe meaning to the first input box in the transaction, whose box ID becomes the token ID, and we call this the issuer box. And then the output box, which then contains the tokens, is called the issuance box. And the EIP will tell you what to put in each of the registers, so that, and like what information to put in order to explain what this token actually is and its purpose. And this is just an example of an NFT minting, so how one could do it. Usually you'll hear sometimes there's a minting fee, but this is, if you were to interpret this literally, this is incorrect. It is really a service or development fee, since it doesn't actually cost you to mint anything. What's costing you money is for someone else to mint it for you. So in this diagram, we have the first box, the green box, the user PK box, which then through a transaction sends money to a proxy address, so some contract, some box with its own custom Ergo script, which just ensures that the money in it gets spent in the correct way. And that's why we call it a proxy. It's sort of like a middleman. Instead of the second transaction, interacting directly with your wallet. And then the outputs of the second transaction would be the issuer proxy. So, telling you what this token is, what it's for, and then its purpose. And then there's also an ErgoPad box, which would be like the fee that ErgoPad would charge for doing this for you. And then the transaction operator box. So if this transaction was run by a bot, we'd want to incentivize the person running the bot. And so we could charge a fee for that. And then not shown, which is implicit, is the miner fee box. And then the last transaction, that issuer box gets used or spent to create an issuance box, and that's where the token will actually be that you want to mint. And this issuance box, if it was some artwork NFT, right, you'd want to send the NFT back to the user. So the address of this issuance box would be the person's public key. But whoever created this minting for you would then set those registers to be the ones necessary, that are defined in the EIP. But the address would be your public key. So you then see the NFT that you minted in your wallet. So in this section, we're going to cover the anatomy of a block. So first, we're just going to, what is a blockchain, right? So, literally, it's a chain of blocks. So it's an off-chain database which holds transaction information at a high level. We have nodes in the network that connect to each other and sync with the one that has the longest chain history. So if different nodes with different lengths of the blockchain, the one that has the longest chain will get used as the official chain, and they download transaction information to their local off-chain database. So like the mempool, for example. Then blocks in the blockchain are used to verify that new transaction information is correct. So any transactions that are included into a block that is mined, and that's part of the blockchain, then that is a legit transaction. And verification of new blocks occur with a mining node or non-mining node, and depending on what sections of the blocks that are used. So we're going to cover at a high level what these different sections are: the header section, the transaction section, the extension sections, and the proofs of EUTXO transformation section. So what is a block? So like I mentioned, it consists of 4 different sections. The header contains general information about the block. The transaction section is the section that holds the transactions that are to be processed and verified by the miner. The extension sections is a new section that's not commonly found in other proof-of-work blockchains, which just lets you hold additional information. And then finally, we have the proofs of EUTXO set transformation. This is proofs of an AVL tree operation performed by a miner on the EUTXO set. So the EUTXO set is sort of, think of it as just some set or bag that holds all of the unspent boxes on the blockchain. And over time, this, if you were to measure the amount of UTXOs in it could shrink and decrease over time as new boxes are created from transactions as outputs, and some other ones are spent as inputs into transactions. And the different sections enable different types of nodes to only download the data they need for verification, instead of having to download all of the past transaction data from previous blocks. So this lets you run an Ergo node that doesn't mine on a Raspberry Pi, for example. So a mining node would have to download everything currently, but if you're just running a node, you only need the header, the extensions, and the proof of UTXO transformation. And the offchain database holds transaction information and the UTXO set. So what are the proofs of UTXO set transformation? So like I mentioned, they're used for verification of the block by other miners and full node verifiers. So it's information about how the UTXO states from the previous block have changed. The order of the set of UTXOs increases or decreases depending on which transaction spent the previous UTXOs in existence and how many new ones were created as their outputs. So what are extensions? They're parameters for miner voting. So like voting on different things for soft or hard forks, miner fee increases, storage rent increases, and other things. So it also holds additional information that's needed for NepoPows to work. So if you're in the future when a wallet holds is using a NepoPows, then it'll need the extension section, and all this is stored in a Merkle tree. The transaction sections is just a list of all the transaction identifiers stored in a Merkle tree. So each transaction gets its own unique transaction ID, and then the block this section holds a list of the transaction ID that are to be included in that block or part of that block if it was mined already. The last section is the header, and this contains links to other sections of the block, and holds other information like the height of the block relative to the current blockchain height, miner votes, and other stuff. Now we're going to go over the anatomy of a wallet. So what is a wallet? Well, recall that each UTXO must have a contract associated with it in R1. So if the box has a pay-to-public key address, so one of the 3 different types, then all boxes that are created with that public key address are associated together. So that's just how I said before that there's a difference between an address and a box. You can create an address without creating a box, but you can't create a box without creating an address. And if you create a box, multiple boxes, each one having the same address, in this case your public key, then we consider your wallet to just be that collection of boxes. So, and a wallet's job therefore is to find these boxes with your public key as its address and show them to you in a seamless way. The next is a little bit more complicated. This is the wallet address hierarchy. So the way it's implemented on Ergo is similar to the same way it's done on Bitcoin, based on this Bitcoin EIP improvement proposal. On Ergo, it's defined in EIP 3. We have the coin type section, which is the string of Ergo characters in ASCII, and then you sum those values together. So each character is associated with a number, and then you sum those together, and that's the coin type number. The change tells you it's an external address only, no internal change address. And the address index is the incremented when creating a derived address. So a derived address is what you can do in your wallet when you even though it's the same wallet, you can have multiple addresses within it. So you'll have a main public key, but then from it you can create like sort of like sub addresses that are still considered part of the same wallet. And the account type isn't used in Ergo, the section. And the difference between external address and internal addresses. So when you create a transaction, and let's say the first input box is your public key, one associated with your public key, so it'll have some amount of erg, but then not all of the erg gets used up in the protocol for what the transaction was for. But since we have to preserve the erg flowing in and the erg flowing out to be the same, then some amount must be returned back to you as change. So currently the way it's done, it will use the same public key used, the same address that was used in the input where the erg came from. An internal change address would be sort of address that's only known to you and would then be used as the change address at the time that a transaction occurs and if change is needed. But this isn't used. And that's it for this video. Thank you.